Hello, my name is Aniket Murhekar. I'm going to talk about our paper titled Constant Factor EFX Exists for Chores. This is joint work with Jugal Garg and John Quinn. So here's the setup. We're interested in allocating a set M of indivisible chores to a set N of N agents. Since the chores are indivisible, an allocation is an M partition of the set of chores into N pieces or N bundles. So an allocation X is specified by the list X1 through Xn, where the set Xi denotes the set of chores given to agent I. So agents specify their preferences over which chores they'd like to receive using disutility functions, which specify the cost of doing a set of chores. So di is the disutility function of agent I, and di of xi is the non-negative disutility or cost that agent I incurs on doing the set xi of chores. Throughout this work, we assume that disutility functions are additive. So the disutility to an agent from a set S of chores is the sum of disutilities to that agent of chores in the set S. So here dij represents the disutility of chore j for agent I. So we are interested in fair allocations. So what is a fair allocation? Perhaps the most compelling notion of fairness is that of NV freeness, where an allocation X is said to be NV free if for all pairs of agents I and H, the disutility that I gets from her own bundle of chores is at most the disutility that she would get if she obtained somebody else's bundle. So she does not covet anyone else's allocation. Now it's clear that NV-free allocations need not exist when chores are indivisible. As you can see from the example on the slide, here are two agents doing 5 chores which they have equal disutility for. In any allocation, the agent with more number of chores will end up envying the other. So in this example, Alice envies Bob. This leads to the relaxation of envy freeness called envy freeness up to any chore or EFX. So in an EFX allocation, Alice may concede that she does envy Bob, so she would be happier if she did Bob's chores. However, this envy would disappear if she removed any single chore from her own bundle. So the envy goes away if she removes this chore, or she removes this chore, or she removes this chore. So formally, an allocation X is EFX if for all pairs of agents I and H, no matter which chore C you remove from I's own bundle, the disutility after removing that chore does not exceed the disutility that I would receive if she had any other agent's bundle. So do EFX allocations exist? It's unclear, it's an open question, and it's an open question even for the simple case of 3 agents. The existence of EFX is considered by some to be fair division's biggest open problem. Perhaps because, first of all, it makes sense as a fairness notion. In the case of indivisible items, it is sort of the best you can hope for. It is the best discrete analog of envy freeness. But somehow it seems to be a challenging question to settle if EFX allocations exist or not. And in a 2020 article in the Communications of the ACM, Ariel Procaccia called it the fair division's biggest open question. Okay. So we have this big open question, which is the existence of EFX allocations. And because we don't know how to solve this in its full generality, the community turned and looked at structured instances, special cases for which there has been extensive work. So there's been a lot of work which showed existence of EFX allocations for special cases like when there are two agents, when there are two types of chores, which is essentially there are copies of two chores, when the number of chores is at most twice the number of agents, and so on. Even for goods, which are items that give positive value instead of which give value instead of disutility, the existence of EFX is open and has been solved in some special cases like 3 agents, 2 types of agents, and so on. So apart from all of this great work on structured instances, there's also a lot of work on another direction by trying to relax this problem in another way, which is that of multiplicative approximations. So instead of expecting that the envy between two pairs of agents disappears exactly after the removal of any item, you settle for the relaxation that the NV is bounded up to a factor of alpha. So formally, for any pairs of agents I and H, no matter which chore C you remove from I's bundle, the disutility to I after the removal of chore C from I's own bundle is at most alpha times the disutility of I for agent H's bundle. This allocation is called alpha EFX. Naturally, smaller the alpha is, the fairer the allocation is. Alpha equals 1 corresponds to exact EFX allocation. But it makes sense to ask what is the best or the smallest alpha for which an alpha EFX allocation exists. And the best known result prior to our work was the existence of order n squared EFX allocations, where n is the number of agents. And along these lines, also there's a lot of work on special cases. For example, when agents agree on the relative order in which they find chores of high disutility, better factor approximations are known. And there are several technical challenges that need to be addressed in coming up with all of these works. But a common theme is that they use laborious case analysis, extensive case analysis to derive these approximation factors, or heavily use the special structure of the instance. This also points to the fact that we really need new general techniques which can apply to more general instances which are not just structured instances, as well as to improve the sort of weak approximation factors that are known so far. So in this work, we look at the question of approximate EFX allocations, and we show the existence of 4 EFX allocations for all instances. And this is a constant factor EFX allocation, which improves the previous result of order n squared EFX allocations by a polynomial factor. So in coming up with this result, the main technical challenge we need to solve is to think about how to aggregate agent preferences. And one central way to do this is to use markets or competitive equilibria, which I will quickly introduce. So in a competitive equilibrium, agents want to earn some amount of money EI by doing chores in exchange for payment. So here chores are attached payments or prices PJ, which specify the per unit, which specify how much money the chore would pay out per unit of the chore. So competitive equilibrium consists of a fractional allocation, which specifies who does what, as well as a set of chore prices or payments, with the intention that agents want to earn this amount of money by doing the least disutility chores that give them this earning. So formally, a fractional allocation Y together with payments P is a competitive equilibrium if the market clears, which means every chore is fully allocated and every agent receives an optimal bundle, which means that subject to earning their required amount of EI, every agent receives a bundle in which they receive the least disutility possible. Now, if every agent wants to earn the same amount of money, then such an allocation is envy free. And in fact, more generally, one notes that the earning of an agent, which is the total amount of money that an agent is earning, serves as a proxy for the disutility, di of yi. Okay, so in a competitive equilibrium, one really gets both fairness and efficiency. One gets fairness if every agent is entitled the same amount of money. And moreover, one can compare disutilities between agents by just looking at the payment, the earning that an agent is getting. So where does this approach fail or not immediately work for us is because this results in a fractional allocation, whereas we are interested in our problem setting in allocating indivisible chores. However, this leads to a natural approach, right? So you start with a fractional allocation, which is fair, which is envy free, because you set every agent to earn $1. So in this example, the blue circles denote agents who each want to earn $1. The red squares denote chores, and on their right are their prices in a competitive equilibrium. The numbers on the edges specify how much an agent is earning from a particular chore. So because every agent is earning the same amount of money, which is $1, the fractional allocation is NV free. So you start with this fair fractional solution and you try to round it. You round it in a way in a way that you get an integral allocation, but the agent's earnings are balanced. Okay. So in this rounding, chores J1 is assigned to agent A1, chores J2 and J3 are assigned to agent A2, and chore J4 is assigned to agent A3. So in this rounded integral allocation, A1 and A3 earn $1.2 and A2 earns $0.6. Now, because A1 and A3 have a single chore, they are EFX because their NV would disappear after removing this single chore from their own bundle. Moreover, A2 earns $0.6, which is the least earning among all three agents. And because the earning of an agent serves as a proxy for the disutility, agent 2 does not envy the other two agents either. So in this example, we started with the fractional NV-free allocation and came up, rounded it to obtain an integral EFX allocation. So does this natural approach work in general? It turns out that it does not. So in this example, where the disutilities of the agents are specified in this table, you again have three agents who are trying to earn $1. And in this example, the competitive equilibrium looks something like this. There is a high price chore whose price or payment is $2. This payment of $2 is given to agent A1 and A2, who both earn their earning requirement just by doing this chore J1. So because its payment is high, it's indicated in red. And agent A3 earns the $1 by doing three chores, J2, J3, and J4, whose price is small, so it's indicated in green. So what happens if you round such a competitive equilibrium? In any rounding, the chore J1 must go to either agent A1 or A2. So if it goes to agent A1, A1 is happy because A1 gets a single chore, so A1 is EFX. A2 is happy because A2 receives no chores. So A2 has a low payment and as a result, no disutility. So A2 does not envy anybody. However, in this rounding, because A2 has a high loss in earning, A3 ends up envying A2 quite a lot, right? Even after removing any chore from her own bundle. So in fact, no rounding of the competitive equilibrium is fair. No rounding of the competitive equilibrium is alpha EFX for any finite alpha, right? So this suggests that this natural approach of rounding the competitive equilibrium does not quite work. So let's pause and think about why this doesn't work. So if you observe, the reason is that there is a high loss in earning of the agents in the fractional allocation compared to the integral allocation, right? So in the integral allocation, an agent is earning too less or too high, whereas in the fractional allocation, they were all earning the equal amount of $1. And this is really happening because the total amount of money that is coming out of chore J1 is $2, which is quite high compared to the earning requirement of any single agent. So both agents A1 and A2 are meeting their earning requirement by just doing the chore J1, right? So how do we fix this? We fix this through the idea of earning restriction. So what happens if we cap the payout from each chore to $1? So instead of allowing each chore J1, a chore like J1 to pay out $2 to these two agents, we restrict it and say that every chore should pay out at most $1. So under this assumption, we still want agents to get an optimal bundle. We still want agents to earn their earning requirement. What sort of an equilibrium do we get? We get an equilibrium that looks something like on the right. So the chore payments or the prices are updated and shown on the right. Chore J1 has a price of 4/3, but it only pays out $1 to the agent. So as a result, only 3/4 of the allocation of the chore is allocated. So this is not a complete allocation, this is a partial allocation. But agent A2 and A3 earn their $1 by doing chores J2 and J3 and J4 in this manner. Now note that in this allocation, compared to the allocation on the left without earning restriction, agent A2 is connected to chores J2 and J3, which are A2's favorite chores, the lowest disutility chores. Now, this information was missing in this fractional allocation on the left because A2 was only connected to chore J1, which is actually her highest disutility chore in the instance. So the insight is that this earning restriction, which does not allow a chore, one chore, to completely satisfy the earning requirement of an agent, it forces agents to seek out other lucrative chores in the market. Okay, so agent 2 will be forced to seek out to meet her earning requirement of $1 by doing chores J2 and J3, which are actually her favorite chores. So it reveals more information about the instance itself. Okay. So concretely, what are we doing? What is an earning restricted equilibrium? Let's start by revisiting what a competitive equilibrium is. In a competitive equilibrium, the market is cleared, so every chore is fully allocated, and every agent gets an optimal bundle, which means it's a bundle of lowest disutility subject to every agent getting their earning requirement. Another way to look at it is to say that every chore whose price is PJ pays out PJ. So if the price or the payment of the chore is PJ, then a total amount of PJ money is disbursed to the agents. So in an earning restricted equilibrium, we modify this condition, the market clearing condition, to say that we impose a cap CJ on the total amount of money that can be disbursed to the agents. And we say that the total amount of money that can be disbursed to the agents is the minimum of the payment or the price of the chore and its cap. That's the only change. That's the only change. It's a simple change. We also have the optimal bundle condition, but it works out great. So does such a solution concept, does such an equilibrium exist? Well, clearly, if the total amount of money that is demanded by the agents is significantly higher than the total amount of money that the chores are allowed to pay out, such an equilibrium, such an earning restricted equilibrium will not exist, right? But surprisingly, we show that this condition suffices. If the total amount of money that the agents want to earn is at most the total amount of is the sum of the chore caps, then an earning restricted equilibrium exists. And the way that we show this is we capture earning restricted equilibria via linear complementarity problem formulation and LCP formulation, and show that a simplex like path following scheme called Lemke scheme terminates at an earning restricted equilibrium. So what about computation? It turns out even without earning restriction, this is a hard problem. The set of competitive equilibria is non-convex, disconnected, and in general, a polynomial time algorithm is open. We do show a polynomial time algorithm for constant number of agents, but in general, even approximately computing an earning restricted equilibrium is an open question, an important open question in our opinion for future work. Okay. So now once we have an earning restricted equilibrium, we set the earning requirements of the agents to $1, the earning caps to $0.50, which entails that no agent can receive their full earning requirement by just doing one chore. They must be connected to at least two chores. And this property gives us a more informative fractional solution, which looks something like this. So here the blue circles denote agents, the green squares denote chores, denoted by the set L, whose price or payment is less than or equal to half being the earning requirement. And the big red squares denote high price chores, denoted by the set H, which is the set of high paying chores whose price is more than half. So we take such a fractional solution and devise a rounding algorithm, which results in an allocation that looks something like this. So every agent receives a set of low paying chores and a set of high paying chores, with the property that every agent receives at most two high paying chores. We also have some properties of this rounding algorithm in terms of the payment of the agents in the resulting allocation. So in the resulting integral allocation X, the earning without the two highest paying chores of any agent, it is at most 1. So remember that in the fractional allocation, every agent was earning $1 fractionally. We show that in the integral allocation, up to the removal of two chores, no agent earns a lot. No agent earns more than $1. So this is an upper bound of the agent's earning. We also show a lower bound on the agent's earning. We show that every agent earns at least half a dollar. Okay. So essentially, these two properties show that the resulting integral allocation is fair in some sense. No agent is doing too little work because everyone earns at least half, and no agent is doing too much work either because up to the removal of two worst chores, nobody earns more than $1. Okay, so this allocation serves as a starting point for computing an EFX allocation, an approximately EFX allocation. Okay. So why is this allocation already not EFX? It's because we remove a chore, the smallest disutility chore or the smallest price chore from an agent uh, before comparing it to another agent to check for EFX. Okay, but well, we notice that agents with no high price chores, no high paying chores are already for EFX. And that's because if you consider some such agent I, who has no high price chores, then the agent earns at most $2 in total because of the earning upper bound. Because of the earning upper bound, every agent earns $1 up to the removal of two highest price chores of that agent. But because this agent has no high price chores, all of its chores are priced less than half. As a result, this agent earns only $2 in total, right? Which is 1 plus 2 times half. At the same time, any other agent H earns at least half. So because prices again are a proxy for the disutility of an agent, because this agent earns at most 2 and every other agent earns at least half, this allocation is 4 EFX for agent I. What this means is that agents with no high price chores, no high paying chores are already 4 EFX. And it suggests that the problematic agents are the ones with more money. So more money, you have more problems. So consider some such agent I who has one high price chore, and I may not be 4 EFX due to the presence of low paying chores. So we don't really have an upper bound on the price Pj of this high price chore J. And once you remove some low paying chore from this bundle, I may still be left with a bundle that has really high price or high payment. And I could envy some other agent L. Okay. So how do we fix this 4 EFX envy of such an agent I? We fix it using the idea of a chore swap. So in an IL chore swap, you identify the agent L who has the least disutility according to agent I. So this is agent I's favorite bundle, the one that agent I would like to do. Okay. Naturally, I 4 EFX envies L. Now in an IL chore swap, you transfer the entire bundle of agent L to agent I and transfer the high price chore J from I to agent I. So this results in an allocation that looks something like this. Agent I retains the low paying chores that she had initially, gets the entire bundle of agent L, and transfers the high price chore J, which was originally allocated to agent I, now to agent L. Okay. Now we prove that after an IL swap, we have locally solved the problem. Agent I is for EFX and agent L is EFX. It's easy to see that agent L is EFX because L only has a single chore. And we prove that agent I is for EFX using the fact that the low price chores bundle were not too costly, and using the fact that L was I's favorite bundle before the swap, and the fact that J was a high price chore. So after an IL chore swap, agent I is for EFX, agent L is EFX. We've locally solved this problem. So this suggests a very natural algorithm, right? You start with this fractional allocation, which is 2EF2 and Pareto optimal, and you repeatedly perform these IL chore swaps. So you identify an agent who is not for EFX, has a single high price chore, identify the agent L who I envies the most, take and perform this IL swap, which entails taking L's entire bundle and transferring the high price chore to agent L. So does it work? Well, not immediately. There are several challenges that can come up. The NV can redevelop in subsequent swaps. Although an IL swap locally solves everyone's approximate EFX NV, this NV can redevelop. Moreover, I haven't specified how to handle agents with too high price chores. So all of these issues need to be carefully addressed, which we do so in the paper. And eventually, we obtain the existence of 4 EFX allocations. Okay. So the main takeaways from our paper and from this talk are that every chore allocation instance admits a 4 EFX allocation. That's the main result of the paper. It improves the previous known result of order n squared EFX allocations, where n is the number of agents. This is a polynomial factor, which we, for the first time, improve to a constant. And we do this by the idea of earning restricted competitive equilibrium for chores, which we believe to have potential further applications for allocating indivisible chores. The computation of such a solution, even fractionally, is an important question for future work. But we do obtain polynomial time computation where when the number of agents is constant. And more generally, I'd like to point out that this is the first relax and round technique for EFX. It's a centralized general approach, and we I believe we do need more such approaches, which work more generally for EFX. Moreover, we also get new results in certain special cases. We also get simpler algorithms that heavily simplify the analysis, the existing case analysis that is used to obtain some existing results. And we hope that these ideas of both earning restricted equilibrium as well as chore swaps can help improve approximation factors for the EFX problem. And those are interesting questions, in my opinion, for future work. So thanks for your attention. Here's a QR code to our paper. I hope you check it out. And I've also linked my webpage below. So thanks for your attention, and I hope to see you at the conference.